In this example, we're supposed to describe the transformations of the function f of x equals the absolute value of x to form the function graph below. So remember, absolute value is a v-shape that usually starts at 0, 0. Looks like that. So to start with, let's look at translations. Normally the vertex sits here. Now the vertex is here. So to describe the transformations of this, we go right 3 and down 1. Those are the translations. Right 3 and down 1. We'll check dilations next. Normally the function goes over 1 and up 1. So normally over 1 and up 1. Right now we are going over 1 and down 2. Since that distance now is 2 instead of 1, that means we do have a dilation. If the distance is still 1, there is no dilation. So this is dilated vertically by a factor of 2. Now, because I'm also going down, that tells me something in addition to that. Because the down part, that tells me it's also reflected. Across. Since it's a vertical reflection, flipping it downwards, changing that orientation downwards, that means that's across the x-axis. And there we go. In this example, we're describing the transformations of the function f of x to form g of x equals negative 5 times f of, in parentheses, x plus 7. And outside we have the minus 3. So going through, to help me with describing the transformations, I'm going to first start out by writing the rules. So inside x, opposite. So I see x plus 7. So we're really going to do x minus 7. And outside y, same. We have times negative 5 and minus 3. Okay, that's done. Let's go ahead and describe the transformations. I'll start with translations and stuff first. So, since we're subtracting 7 and subtracting 3, there's translations. So we're translating subtracting from the x values will create a translation left, 7. And subtracting 3 from the y values will create a translation down 3. Remember that addition, subtraction is translation. Multiplication is dilations, and multiplying by negative is reflections. So in addition to translation, we have 2 other things going on. We are multiplying by negative, and we're multiplying by a number that's not 1. So any number that's not 1 creates a dilation. So we're dilated vertically, since it's affecting the y values, by a factor of 5. And in addition, since I am multiplying by a negative 5 instead of just a 5, that also gives me a reflection across. Since this is affecting the y values, it's actually across the x-axis a change in the y value, for instance, 1, 2 to 1, negative 2, you can see it flips it across the x-axis. So if it affects the y values, it flips it across the x-axis. And if it affects the x values, it flips it across the y-axis. But reflected across the x-axis. And that's it. So in example 3, given the domain between negative 10 and 4, with 4 being included, and the range between negative 5 and infinity, with negative 5 being included, of f of x, and the equation for g of x is negative 3 times f of, in parentheses, x plus 3, and we have our plus 1 outside. State the domain of g of x. So here is the original domain and range. I'm just going to jot it down. Okay. Now, since the point of this is to use transformations, we can apply transformations to the domain and range and get the modified or the domain and range of g of x. So let's figure out the rule. Inside x opposite, let's see x plus 3, which means we're really doing x minus 3. And outside y same, I have the negative 3 and the plus 1. Negative 3 is connected by multiplication. So y times negative 3 plus 1. Now that we have that, we can apply it to our graph, or our, not graph this time, our domain and range. So let's start by doing the x values. Remember, this is domain, so these are both x values. We're going to subtract 3 from both of them. Negative infinity minus 3, well, that doesn't really change anything. It's still negative infinity. And 4 minus 3 is 1. For range, we have a little bit more complicated rule. It's multiplying by negative 3, then adding 1. So, remember that they're both y values here. If we do negative 5 times negative 3, that's positive 15. And then plus 1, it's positive 16. If we do infinity times negative 3, well, normally infinity times 3 is still infinity. But because we're doing a positive times a negative, the result overall is negative. So, positive infinity times our negative 3 will result in negative infinity. To combine those two facts. We have a problem though with our range here. When you do range and domain using the interval notation, the smaller number has to come first. So you can see that whenever we multiply that negative for the range, it changed which one was smaller. So we're going to have to just rewrite it one last time for the range as negative infinity to 16. Negative infinity is not included, but the 16 is. And there we have it. So we have the domain of G, and we have the range of G. So state the domain and range, intervals of increasing, and the decreasing intervals for the function f of x equals 2 times the absolute value of x plus 1 minus 3. So there's two ways we could go about doing this. Both of them require the use of transformations. One involves giving a rough sketch of the graph. The other doesn't. So we're going to go ahead and do a rough sketch of the graph. And you don't need anything too detailed to do this. Really, when you're doing this, you really just need the vertex, and then whether the function is going up or down. You don't even need to care about the dilations here. You just need to know if it's been reflected or not. So if we go ahead and try to find where the vertex is, to get us started, inside x opposite, so x minus 1 is our rule. Outside y, same. So we're going to do y times 2 minus 3. The vertex, remember, is that point, which is the ordered pair 0, 0. If I apply my rule, x minus 1, so negative 1, comma, y times 2 minus 3, so y times, or 0 times 2 is 0, minus 3 is negative 3. The vertex, since it starts at 0, 0, is never affected by the dilations or reflections, so it never is affected by the multiplication for the absolute value function here. Now that we have that, we can plot that point. Negative 1, negative 3 is over on the left here. We'll just use this as my negative 1, negative 3. And again, it doesn't have to be a detailed graph. You really just have to know the x and y values where that vertex is. And then we also have to know whether it's been reflected or not. Since we're multiplying by a positive 2, that means we're not reflecting it. So the V shape is still up and down. I mean, it is going to be stretched vertically. But that's not going to affect domain range increasing or decreasing. The only thing that would is if there's a reflection there. So we have our rough graph, and this is actually enough to do domain, range, intervals of increasing intervals, and decreasing intervals. So let's go ahead and get started. Starting with domain, absolute value functions are nice because their domain is always all real numbers, or if you prefer negative infinity, less than x, less than infinity. You can check it like we used to, but that is the domain for absolute value functions, unless you're intentionally restricting it. Range is not so nice, but if you go from the bottom, you would first get to the graph at that point, at that vertex, and you can see that that's the y value of negative 3, making sure you use the y value from the vertex. This is why you don't really need a very detailed graph. So negative 3 is our y value, because it's actually a solid line, solid dot. It's less than or equal to. And then from the top, we hit it, it runs off positive infinity. So that's domain and range. For intervals of increasing and decreasing, you separate that at any highs or low points. So for increasing and decreasing, we separate at any high or low point, which again happens to be the vertex. So we would separate the graph right there. So the two regions are negative infinity to negative 1. You can tell that because of the x value in the vertex. Remember, the intervals are using x values here. Then negative 1 to infinity. Once we have the two regions, we just have to figure out which one is decreasing, which one's increasing. That's always from left to right. So as we go from left to right, the left side is going down. So that's the decreasing interval. And the right side is going up, so that's the increasing interval. Remember, depending on if there's highs or lows, there may or may not be more than one interval. It could just be one interval, it could be 2, it could be 72. It all depends on the shape of the function. That's how you go about doing it with a rough sketch of the graph. You can also do it with transformations directly, but I'll do a separate video for that. Okay, so we're going to do the same example, but I'm going to go over how to do it with transformations directly. This does require a little bit of knowledge about what the parent function looks like, and then how to apply transformations directly to domain, range, and stuff like that. So I know domain and range of the parent function, which is normally negative infinity less than x less than positive infinity. And range is normally 0 less than or equal to y less than infinity. Remember the absolute value function looks like this normally. We're applying the transformations, and I already have the transformations written out earlier. So I'm not going to go through doing them again, but we're subtracting 1 from the x values. If you subtract 1 from the upper and lower bounds of domain, it's not going to change anything. Negative infinity minus 1 is still negative infinity, and infinity minus 1 is still infinity. For the range, we're doing two things. We're multiplying it by 2 and then subtracting 3. So 0 times 2 is still 0, minus 3 is negative 3. And then infinity times 2 is still infinity, minus 3 is still infinity. So you can see we end up with the same thing for domain and range. For increasing and decreasing, it's a little bit more complicated, but you can still do it with transformations. So normally the graph would be split right down the middle, right down the y-axis, into two regions, negative infinity to 0, and 0 to infinity. Now because of our transformations, these two intervals will change into, well, we're subtracting 1 from the x value. So negative infinity minus 1 is still negative infinity. 0 minus 1 is negative 1. Remember, these are intervals. They're both x values there. 0 minus 1 is negative 1. Infinity minus 1 is infinity. Remember, everything was x values. For the y descriptor, that's just the words increasing, decreasing. So originally, the first interval is decreasing. The second one is increasing. This will only change if there's a reflection in the graph. Since there is no reflection for this, the decreasing one stays the first one, and the increasing one stays the second one. So increasing is negative 1 to infinity, and domain, or decreasing one, is negative infinity to negative 1. And you can do all of this without ever having that graph actually there. You don't need this graph here to actually do it. So long as you can picture it in your head, you can jump straight to the domain and range without ever actually looking at a graph. As long as you understand transformations and understand what the parent function actually looks like and its characteristics.